In this video, we continue with chapter 6.3 and take a look at composition of linear transformations. So our learning objective for this video is to find the standard matrix for the composition of linear transformations and to find the inverse of an invertible linear transformation. So let's take a look at the definition of the composition of linear transformations. So the composition of T, where T1 maps Rn to Rm, and T2 maps Rm to Rp, is written as T of V equals T2 of T1 of V. So T1 acts first and then T2 acts second. V is a vector in Rn, and we denote our composition here as T equals, we say T2 composed with T1. So when we do our composition, the T2 comes first because it's the last acting function. And then we note the domain of T is the domain of T1. Moreover, the composition is not defined unless the range of T1 lies within the domain of T2, as we see in this diagram here. So notice here's T, our outer function, and T takes us directly from Rn to Rp. And so you can kind of think about this as like T1 and T2 are like shorter flights along the route. So T1 takes us from Rn to Rm. So we go from V to W. And then T2 takes us from Rm to Rp, from W to U. So it's important to note here that composition is not commutative. And that's because matrix multiplication is not commutative. We're going to see in the next theorem that we can represent composition as a series of matrix multiplications. So we can generalize to a composition of 3 or more linear transformations. So for example, if T is T3 composed with T2 composed with T1, that's going to be defined by T of V is T3 of T2 of T1 of V, and it's going to be represented in terms of matrices as A3 multiplied by A2 multiplied by A1. Let's take a look at theorem 6.11. So theorem 6.11 says we're going to let T1 map from Rn to Rm, and T2 maps from Rm to Rp, and these are linear transformations with standard matrices A1 and A2, respectively. So standard matrix A1 is associated with linear function, and standard matrix A2 is associated with linear transformation A2. So the composition T mapping from Rn to Rp, defined by T of V equals T2 of T1 of V, is a linear transformation. So moreover, the standard matrix A for T is the matrix product A2 multiplied by A1. And we got to make sure that our matrix product is in the same order as our composition. So let's take a look at the proof. So to show that T is a linear transformation, we're going to let U and V be vectors in Rn, and C is going to be any scalar. So T1 and T2 are linear transformations. So we can say T of U plus V is going to be this composition T2 of T1 of U plus V. And so then we can say, okay, well, we've got T2 of T1 of U plus T1 of V, and then we can say, well, we can distribute that through. So we've got T2 of T1 of U plus T2 of T1 of V, and that's just T of U plus T of V. And so we have shown that this is closed under addition, or the linearity property here. So now let's look at the scalar multiplication. So C is any scalar in R. So we've got T of CV. So that's going to be T2 of T1 of CV. And we know we can pull the C out here in the second row. So we can say T2 of C multiplied by T1 of V. But then we can further pull the C out. So we get C multiplied by T2 of T1 of V, which is just scalar C multiplied by T of V. All right, so now to show A2 multiplied by A1 is a standard matrix for T, we use the associativity property of matrix multiplication, and we can write this last row here, that T2 of T1 of V is equal to T2 of A1 of V, because A1 is the standard matrix for linear transformation T1. And then we can write, well, that's equal to A2 of A1 of V, since A2 is a standard matrix for linear transformation T2. And then using associativity, we can say, well, this is just A2 times A1 multiplied by V. So let's take a look at an example here. So we are given the linear transformations where T1 maps from R3 to R2 and T2 maps from R2 to R3, defined by these here. This should say T2, note my little handwritten correction here. So here is A1, and here is A2. And since T1 maps from R3 to R2, A1 is a 2 by 3 matrix. And since T2 maps from R2 to R3, A2 is a 3 by 2 matrix. And so we want to find the standard matrix for T, which is T2 composed with T1. So we just multiply. So here we go. A2 times A1 is going to give us a 3 by 3 matrix that corresponds with the composition of functions. All right, a linear transformation T1 from Rn to Rn is invertible, and notice it has to go with the same dimensions because we have to have a square matrix. It's invertible if and only if there exists a linear transformation T2 from Rn to Rn such that for every V in Rn, T2 of T1 of V gives us back out V, and T1 of T2 of V gives us back out V. So then we can say T2 is the inverse of T1. And this matches what we know about inverse functions back from pre-calculus and calculus class. So when the inverse exists, it is unique, and we denote it by T1 inverse. So theorem 612 is about the existence of an inverse transformation. So we let T map Rn to Rn be a linear transformation with standard matrix A. So then these following three conditions are equivalent. So it's equivalent for T to be invertible, T to be an isomorphism, and A to be invertible. So if T is invertible with standard matrix A, then the standard matrix for T inverse is going to be the matrix A inverse. So let's take a look at the proof here. So let's look at how statement 1 implies statement 2. So statement 1 here is that T is invertible. So we're saying that T is invertible implies that T is an isomorphism. So we're going to let T be invertible. If T of V1 equals T of V2, then T inverse of T of V1 is going to equal T inverse of T of V2. So that's going to give us that V1 equals V2. So T is 1 to 1. Remember to show that a function is an isomorphism, or the linear transformation is an isomorphism. We have to show that T is 1 to 1 and that T is onto. So we just showed T is 1 to 1. And so now we want to show T is onto, and that's because for any W in Rn, T inverse of W equals V satisfies this equation that T of V equals W. So if T is invertible, we just showed it's both 1 to 1 and onto. So let's take a look at 2 implies 1. So that's saying if T is an isomorphism, that implies that T is invertible. So let T be an isomorphism, and then we define T inverse as follows. So because T is onto, for any W in Rn, there exists V in Rn such that T of V equals W. And then because T is 1 to 1, this V is unique. So we define the inverse of T by T inverse of W equals V if and only if T of V equals W. And then we have our corollaries from theorems 6.3 and 6.4 that we saw earlier. And so that shows that the isomorphism and A being an invertible matrix are equivalent. The corollary for theorem 6.3 is back in section 6.4. And so that's the corollary that said if T maps Rn to Rm is a linear transformation T of X equals matrix A times vector X, then the kernel of T is equal to the solution space of AX equals 0. And then the corollary to theorem 6.4 was the one that said then the column space of A is equal to the range of T. So that shows this equivalency between T being an isomorphism and A being invertible, because we have the column space equal to the range, and we have kernel equal to the solution space. Okay, so if T is invertible here on our last line, then T of X equals matrix A times vector X implies that T inverse of T of X equals X, which equals A inverse multiplied by A of X. And so the standard matrix of T inverse is A inverse. So let's take a look at this example. So given the linear transformation T mapping from R3 to R3, defined by this function here, we want to show that T is invertible and find its inverse. So the first entry here is just X1. So then our first row here of matrix A is going to be 1, 0, 0. So I could go through the multiplication of, T of 1, 0, 0 and get out my values here. This would give me 1, 2, and 3 that would correspond with this column here. So you could write these as columns and build matrix A that way as well. But I'm just going to use the coefficients here. So the next entry is 2x1 plus x2. So in row 2, we get a 2, a 1, and a 0 because there's no x3 component in the second entry. And then the third entry here is 3x1 plus x2 plus x3. And that gives us a 3, 1, 1. And if you wanted to find the other two columns using the standard bases, you would calculate out T of 0, 1, 0. And that's going to give you that 0, 1, 1. And then you do T of 0, 0, 1. And you'd see the only place x3 shows up is in this third entry. So that gives you that last column, 0, 0, 1. So you could do it either way, but it's much, much faster to just pull the coefficients out of the linear transformation and associate those entries, coefficients with each of the rows of matrix A. And then we can find A inverse. You can use SIMPy to find this and verify that A inverse is this matrix 1, 0, 0, 0, 1, negative 1, and 0, 0, 1. So we can find the inverse by finding the inverse of the standard matrix. Okay, in our next video, we are going to take a look at continuing on using the standard matrix to do calculations with non-standard bases and general vector spaces.